As you might expect, faculty get a fair number of emails from students over time, and I wanted to share with you one that I got recently that somehow made it past my spam filters, because it's relevant to the stuff we're talking about right now. And it says, Dr. Orvis, I'm confused. Earlier you said that the energy needed to manipulate a magnetic nucleus in an external magnetic field depended upon two things. The value of that magneto-pyric ratio thingy, and the bucks you had to buy a big old magnet. That's what gives each magnetic nucleus its own frequency of light needed to change it in the magnetic field. But now you come along and say that each group of hydrogens in a molecule has different chemical shifts, which means different frequencies of light to manipulate them. I thought all hydrogens were the same one proton nucleus with the same ratio, no matter what molecule they're in. I can only conclude that either 1, you lied to us, 2, you're an idiot who doesn't know what he's talking about, or 3, there's something else going on. So what is it? Signed, a student. Oh, and P.S. Love the shirts. Whenever I get an email like that, my first instinct, of course, is to say, kill. However, I think we'll run with option 3. There is indeed something else going on here. That something else that's going on, of course, are the electrons. They are all paired in almost every sample that we take a look at, so they're not generating an overall magnetic field. But they are charged particles, they are in motion, they are spinning. So they do have magnetic effects. Technically it's called diamagnetism, and it is essentially how the resistance of most diamagnetic materials, which is most non-magnetic materials, to an external magnetic field. To see this, look at this little wafer of graphite, one of the most diamagnetic materials known. It's actually floating over these little neodymium magnets here. The resistance of the diamagnetism is strong enough to actually overcome gravity in this case. Now the molecules in my hand, of course, are diamagnetic, and if I put a large neodymium magnet in my hand, you'll notice it's not really floating. There is a resistance, if you will, of the diamagnetism in my hand for the strong magnetic field of the neodymium magnet, but in this case it is not strong enough to overcome gravity, and in fact it rarely is. This is a pretty weak effect, and it's very difficult to actually see it. Graphite, being one of the most diamagnetic materials we know of, does make it possible to see. If you want to do yourself a favor and see another example of this, go Google the phrase magnetic levitation of a frog. Go ahead, give it a try. I'll wait. So in theory, a proton is simply a proton is a proton is a proton. Every nucleus, every hydrogen, and every molecule we look at is indeed exactly the same. And so in theory, it ought to take exactly the same amount of energy to manipulate its magnetism in the external magnetic field. We've pictured this situation with little diagrams like this one before, and all of those statements are perfectly true. They are, however, slightly incomplete. In real molecules, every proton in our samples that we look at are also surrounded by clouds of electrons. With their opposite charge, with their motion, they generate diamagnetism that opposes the external magnetic field. And so we will often say what each individual proton feels in a molecule is not necessarily B naught, the big honkin' magnetic field, but what is sometimes referred to as B effective, the big honkin' magnetic field minus the diamagnetic contribution of the electrons. And the interesting thing about it is that contribution can change, mainly because the electron cloud around each of our nuclei can be different. Some nuclei have thick electron clouds around them because they may be distant from any electronegative atoms. Some nuclei may have relatively thin electron clouds around them. Some of the electron density pulled away by electronegative atoms. Since the electron cloud decreases by a tiny bit the strength of B naught, the big honkin' external magnetic field, we often will say the electron clouds shield the proton. And so if you have a proton that is on the up upfield side of the spectrum. That is a proton with a thick cloud of electron density around it. That is a highly shielded proton. Those that are downfield are said to be de-shielded, have a thinner electron cloud around them. I often find it useful to think about it in terms of two possible extremes. On one side, you have the bare proton, an H plus, from, let's say, the strongest acid you can imagine. This is a proton without any electron cloud around it at all. It is magnetic. In the external magnetic field, it will feel the full effects of B naught. It will have no electron cloud to make any changes, and we can manipulate its orientation in the magnetic field with a photon. On the other extreme, however, we have, let's say, hydride ion, H minus. Now, this is a proton, but it has a thick, rich electron cloud around it. This is a fairly shielded nucleus. Now, what it's going to feel is, of course, the big honkin' magnetic field B naught, but it will be modified slightly by the dimagnetism of the electrons surrounding it. And so its B effective will be slightly less than B naught. And it will take a slightly different frequency of light, a slightly different energy to manipulate the magnetic orientation in the external the nucleus orientation in the external magnetic field. This graphic tries to, give a feel to that. It's slightly simplistic, but it captures the basic idea. Imagine, if you will, in the very middle of your spectrum on our instrument, that would be exactly 400.000 megahertz. That's where a nucleus will change its its orientation in the external magnetic field. On one side, you have the highly de-shielded bare proton. On the other, the highly shielded hydride ion. The de-shielded bare proton, it's going to take slightly more than 400 megahertz frequency energy to change its orientation in the external magnetic field. Now, I'm not talking 420 megahertz. I'm talking 400.00001 megahertz. It is a tiny effect, but it is measurable. On the other side, on the upfield side, we have the highly shielded hydride ion. Here, it's going to take slightly less than 400 megahertz to change its orientation in the external magnetic field. Again, I'm not talking 390 megahertz, I'm talking 399.9999 megahertz. A tiny effect, but it is measurable. And so overall, yes, we will say protons in our magnet, B naught that we bought, with their own magnetogyric ratio can be manipulated in the external magnetic field at 400 megahertz, plus or minus a tiny amount given by the shielding of that nucleus. You can express it in a couple of different ways. I've seen it expressed as the frequency plus or minus a tiny amount due to the shielding. I've also seen the Lamore equation altered slightly with a new term. I've seen it referred to as a sigma, called the shielding constant, that changes ever so slightly the frequency that it takes to manipulate a nucleus in the external magnetic field. Now, the shielding constant is very tiny compared to the overall strength of the magnetic field, but it is enough to make each group of nuclei, each group of protons that we see, or C13 or other magnetic nuclei, slightly different. And that difference is what we call the chemical shift.